Okay, good morning, ladies and gentlemen. Okay, this is Professor David J. De Los Reyes. Okay, the date for today is June 17, 2024, and the time is around 12:47 a.m. Okay, my topic for this morning will be a continuation of my long video format topic. My long video format topic is actually my ninth complete subject or complete syllabus. This is DC circuit. So our topic for this morning is DC circuit lesson number 10. This is a long video format topic. So for this morning, we'll discuss or tackle Thevenin's theorem. Okay, let's proceed. The title of the subject matter for this morning will be DC circuit lesson number 10, and this is Thevenin's theorem. Thevenin's theorem is actually, sorry for this one of the solution of circuitry in which if we are given a circuit and the problem is asking for the current passing through that portion of the circuit, actually we could present a solution by using the so-called Thevenin's theorem. The last time around, I discussed the so-called Kirchhoff's voltage and current law and the so-called computation of current passing through any portion of a circuit. And the next topic after that is actually by using the so-called total resistance method. And by using the two solutions from the previous discussions, actually we came out with the same answer. The current passing through the 3 ohm load, assuming the same problem, okay, is actually 1.14 amperes. So for this morning, I will be giving an example problem by using Thevenin's problem, solving the same problem, and supposed to be what will come out for the final answer will be same as from the previous two solutions, 1.14 amperes. Okay, let's try to discuss Thevenin's theorem. Thevenin's theorem is just actually one of the smartest solution in the so-called computation of current passing through any circuit. If we are given a circuit, an active circuit meaning it got a voltage source inside, and there are two terminals emanating from the active circuit. And supposed to be, we will connect a certain load at this terminal. The problem is asking maybe what will be the current that could be drawn from this active circuit. And the solution will be by using Thevenin's theorem. So we could visualize Thevenin's theorem. We'll now proceed with the so-called example problem. Okay, to illustrate the concept of Thevenin's theorem, this is actually the final concept of Thevenin's theorem, but I would like to bring out an example problem. The same problem as from the two previous what do you call this lesson number 8 and 9, same problem. So we are given a DC circuit. That's why DC circuit, this is a DC circuit. The voltage source is DC, right? Battery. 1 ohm, 2 ohm, 4 ohm. This is 3 ohm, 5 and 6 ohm. The problem here, okay, so we could visualize the correctness of our theorem or our solution. We will be presenting a same problem, okay, and our motto here is to bring out the same current as from the two previous solutions. So the problem here is asking what will be the current passing through the 3 ohm load. Okay, what will be the current passing here, okay, by using Thevenin's theorem. Okay, to bring out the so-called Thevenin's theorem, like what I said, there should be an active circuit. Okay, so what we'll do is I will try to erase this one. I will remove the 3 ohm load. Okay, I will remove it. So there is a terminal A here and terminal B. So it seems this terminal A and B is actually the one emanating from the active network, right? Okay? And what will be the configuration of the circuit inside? Whatever the configuration that was given in the problem, that's the configuration inside. There's a voltage source and there are resistances inside. Okay? So if we try to disconnect, hold on. I will erase this one so it will look neat. Okay. I remove the 3 ohm load. So it seems I got 2 terminals, okay, coming out, right? And the configuration inside now will be, there's a 12-volt source, okay? After the disconnection of the 3 ohm load, all the resistances are now actually in series. That's the configuration now, right? So that's an easy part of the solution now. Okay, so to compute for, what do you call this, the voltage across this one, because the number one step here is actually to compute for ETH. ETH is the open circuit voltage. Like what I said, if this is the active network, if there is 2 terminals coming out here, if we try to measure the voltage across this by using a voltmeter, what will supposed to be the voltage that will come out? But theoretically speaking, if we try to compute for the voltage across this, we will be using our knowledge of so-called DC circuit, Kirchhoff's voltage and current law, and in this whole computation of the resistances. We all need those ones, okay? So after the disconnection of the 3 ohm load, this will now be the configuration. And if we try to get our voltmeter here, the voltage across this is actually ETH. Okay? It is the open circuit voltage for a Thevenin theorem. And to compute for the voltage across this, that's an easy one now. Okay? We'll just compute for the current circulating, and we will be applying the so-called Kirchhoff's voltage law. We could compute for the voltage ETH. So to arrive at ETH, we'll solve first for the total resistance. After the disconnection of the 3 ohm load, all the resistances are actually in series. So the total resistance now will be the summation of 1 plus 2 plus 4 plus 5 plus 6. After the disconnection of the 3 ohm load, these are all in series. And the total value is 18 ohms. Okay? So if we know the total resistance, we know the applied voltage 12 volts, we could compute for the circulating current. And the circulating current will be, it is by using voltage equal to IR, right? So I will be equal to voltage over R. The applied voltage will be 12, and the summation of these 5 resistances is actually 18. That will be over 18. So we could compute for the circulating current 0.67 amperes. So we now know the circulating current. And if we know the circulating current, okay, the voltage across this one should be this 12 volt source here, minus the voltage drop here, minus the voltage drop here. So I place it here. ETH, the subscript TS refers to Thevenins. Okay? ETH is E with subscript TH is actually the Thevenin's open circuit voltage. Okay, we know the Kirchhoff's voltage law already. The voltage across this will be this 12 volts here, minus the drop here, minus the drop here. So it will be 12 minus I times 1 ohm, minus I times 5 ohm. So this is 12. Okay. I is the same, so this will be 0.67. And 1 plus 5 will be 6. And if we try to subtract, the value of ETH is actually 7.90 volts. And the meaning of this, it's the open circuit voltage. Okay? It's the voltage across these terminals A and B after the disconnection of the 3 ohm load. Okay? that will be the voltage that will come out here. Theoretically speaking, in actual, we just stop our voltmeter here, it will come out to be 7.19 volts. Next step, we solve for capital letter R, we subscript TH. And this is termed to as the short circuit, what do you call this, open circuit voltage. Open circuit, resistance. Open circuit resistance. Like on the voltage, if we try to measure the voltage here, we will be using the voltmeter. For step number 2, for the reading to be resistance, it should be an ohmmeter, but there is a precondition for that one. We must have to short the 12 volt source. Okay, we will short out this one. So if we try to short out this one, it seems this 12 volt is gone. Okay, and the voltage, the value that we could measure here is termed to as RTH, the open circuit resistance. The condition before taking this one, try to short out the given voltage source. Okay, so solving for RTH, we short the 12 volt source. So if we short it, no more 12 volts here. This is just a complete line. So if we try to get our ohmmeter here, okay, what will be the voltage, the resistance that will come out? Theoretically speaking, we could do it. Okay, if we try to put our ohmmeter here, this 1 ohm and 5 ohm are in series, and this 2 ohm, 4 ohm, and 6 ohm are actually in series also. So I place it here, the single equivalent of this one is RE1. They are in series, right? So it will be 6 ohms. And the single equivalent of 2, 4, and 6, they are all in series also. It will be 2 plus 4 plus 6, and this will be 12 ohm. Okay, and what will come out will just be simply like this. Hold it for that. What's happening? Right? This is RE1, this is RE2, okay? This will be RTH. Okay? RE1 is the single equivalent of 1 and 5, and RE2 is the single equivalent of 2, 4, and 6. So after the compression, RE1 and RE2 are in parallel. So if we try to compute for the total resistance across these, there are 2 resistances in parallel, so we will be using the formula product all over the sum. So if we try to take the single equivalent RTH now will be the product all over the sum for 2 resistances in parallel. And what will come out will be 4 ohms. And this R with the subscript TH is actually the Thevenin's open circuit resistance. The open circuit resistance. Okay? That's step number 2. We know already, or we have computed already the open circuit voltage. We computed already the open circuit resistance. So to compute for the current passing through the 3 ohm load, we will be drawing the Thevenin's equivalent. And the Thevenin's equivalent is termed to as the so-called constant voltage source. This is ETH. In series with it will be RTH. Okay? And the terminals in which the load in which the current will be known is actually at point A and B. Actually, we disconnect it here, right? So after taking the value of ETH and RTH and they're actually in series, you try to reconnect the 3 ohm load. Try to reconnect. And if we try to reconnect, what's the configuration now? It's just a simple series circuit now. This RTH is in series with this. Okay? And so it seems we are just given a simple circuit now. So the total resistance now will be 4 ohms plus 3, and this will be 7 ohms. So the single equivalent of this will be 7 ohms. And the applied voltage is 7.98. So the current passing through the 3 ohm load now, I with the subscript 3 ohm, meaning the current passing through the 3 ohm load now will be ETH the computed value of the open circuit voltage all over the single equivalent of RTH and the 3 ohm load, which is 7. So this is 7.98 over 7, and what will come out is 1.14 amperes. Okay? So by using Thevenin's theorem, the current passing through the 3 ohm load is actually 1.14 amperes. It is the same as from lesson number 8 and number 9. Lesson number 8 is actually by using Kirchhoff's voltage and current law in the computation of this. Lesson number 9 is actually by using the total resistance method. It is also 1.14 amperes. And by using the Thevenin's theorem, it is also 1.14 amperes. Okay, that's it, guys. So for those of you who would like to watch my channel comprises of long video format topics, and one of the long video format topics is actually this circuit. So if you would like to watch my channel, you will learn something from it. Okay, good morning from Los Angeles. This is Professor Thevenin.